All right, so let's do this. All right, so now we're going to be talking about operations with complex numbers. If you guys don't know what a complex number is, a complex number is the square root of -1. That's that imaginary number. You can't take the square root of a negative. The reason being is if I do -1 times -1, I get +1. There's never a situation where you can square a negative number. The only way to get -1 would be 1 and 1, which isn't a squared. You're not squaring anything, you're just multiplying it. So it's impossible to get a negative square root. So that's where they invented imaginary numbers. So in this lesson, we will identify complex numbers. So I take it we're going to learn what complex numbers are, and we're going to apply it to arithmetic to simplify equations that contain complex numbers. So we're going to find ways to simplify things. So for example, if I had like 2 plus 4i divided by 2, you can probably simplify this to just, oops, not that. Oh, you guys are lucky. This was like super off last time or in the last class. I guess closing Edmentum helped. So you can simplify it because of the fact that it would reduce into this. You can always split your numerator, your top number. You cannot split your denominator. The reason being is think about this. 1, 1. 2/3 is the same thing as, I am super off today. I think it's because Nelson forgot to do the meme. So because Nelson forgot the meme, I'm off my game. So 1/3 plus 1/3 is 2/3. That makes sense. But if I have something like, I can't do something like this. Splitting the denominator doesn't work because this is 2 plus 1. It's not 2/3. So you can always split your numerator, just leave the denominator the same, but you can't split a denominator leaving the numerator the same. They're two completely different things because of division. So let's get into this. So irrational numbers. So an irrational number is a number that can't be done with a fraction. So for example, pi. Pi goes on forever. I think this number right here, the 6.28, I think that's 2 pi. Let me check. Is there a pi on this calculator? Why is there no pi on this calculator? Desmos.com/scientific. I found that there's limitations to Desmos's calculator doing, or to Google's calculator in my pre-calculus class, so I started using the Desmos calculator. So desmos.com/scientific is the Desmos calculator. So 2 pi. Yep, looks like that's 2 pi. So this is irrational numbers. There's no way I can make a fraction that will make this number. It's irrational. Same thing with square root of 6. I believe that goes on forever. Square root of 6. Yeah, see, there's no repetition. It just goes on. It's irrational. Rational numbers are anything that can be done with a fraction, which is basically everything. So I'm going to do integers first because integers are less broad. Integers are just whole numbers. Real numbers are just that. They're numbers that are real. So that can be anything basically. And then we can do rational numbers. So these are anything with a fraction. So for example, this 0.245, that can be written down as over 100 because the 5 is in the hundredths place. So that's where we get these names, the tenths place. This is in the tenths place because it's 2/10. This is 24 hundredths. This is 245 hundredths. Or actually, it's thousandths. Whoops. Totally messed that one up. Thousandths. So tenths, hundredths, thousandths. And that's why there's no ones place, because there's only a one place. You can't really divide by one. So the ones place and the one place are the same thing. All right, and that should be it. Yep, got them all right. Like I said, it's a little weird. I was thinking this one, but then I'm like, wait, there's a pi right there. That can't be a rational number. It is a real number, but it's not a rational number. So irrational numbers can be real numbers. Rational numbers are obviously real numbers. Integers are real numbers also. Real numbers covers a lot of it. We just have never done imaginary numbers yet. They call them complex because complex numbers can have a real and an imaginary. So that's why this section is called Understanding Complex and Real Numbers. All right, so irrational numbers go on forever. Imaginary numbers are these. They're i's and negative roots. Negative roots are imaginary numbers. That's the whole basis for it. Complex numbers have both. It's a combination of a real and an imaginary. If you want to see the hierarchy, there's numbers, real numbers, imaginary numbers. Then there's rational numbers, irrational numbers, integers, non-integer fractions. Integers can be spaced out between whole numbers and negative numbers. Whole numbers can be 0 or natural numbers. So natural numbers are 1, 2, 3, 4. So you can always, I like clicking on these to kind of get more information. Real numbers, any number that's not imaginary. Great definition there at Mentum. What's real? Anything that's not imaginary. Nelson, wake up. Anyways, until now, we've seen when we square numbers. So whenever we're squaring a number, we get this positive 1. Logical conclusion of that pattern is that there is no number whose square will result in a negative number. So how do we deal with that? We made up this number, the square root of negative 1. When people first developed numbers, they used to use natural numbers. So natural numbers are 1, 2, 3, 4, 5. And then we started discovering things like fractions, square roots, and pi. Those do exist. They're real. But I squared equals negative 1. That's funny. So it's this idea of like getting this negative 1. So they don't really exist. When with research and discoveries, we found that imaginary numbers are in fact very useful in fields of math, science, and engineering, for example, electrical. So they use this a lot in electrical engineering. The reason being is if you square an imaginary number, all of a sudden it becomes real. So they are used. I'm not too familiar with it, but I know they use it in electricity a lot. Just to keep track of when things are off, it's an imaginary number. When things are on, they're real numbers. So when you square something, it makes it a real number again. It helps with like engineering and electricity. Like I said, I don't know too much about that. I haven't really done engineering. So by the time we found real life uses for imaginary numbers, their name had stuck. So yes, they're called imaginary numbers, but that's just their name. That's why we keep calling them that. We haven't really given them another name since then, but imaginary numbers do have a lot of uses. This is very lecture heavy. I thought we would be doing a little bit more practice. As always, guys, make sure you watch the videos. They do help out a lot, especially this chart right here. I really like this chart because we'll see that they keep repeating over and over again. So these are the only ones. Once we have I to the fourth, these things are going to repeat. So that's, like I said, I don't cover it because you guys really, really should be watching these on your own. They are really helpful. These numbers will repeat forever, and they'll show it to you if you watch it. All right, so if we're doing this, I to the 32, so assuming we already knew about this, so I is square root of -1, I squared is -1, I cubed is -1 times I, so it's -I, and I to the fourth, that's just a repeat of I0. So I to the fourth is just I squared times I squared, -1 times -1, that's a +1. So they'll keep repeating. What happens if we have I to the fifth? I to the fifth, well, that's just I. 1 times I is I. So what we do is we're going to divide our expression by 4. If we do not, and we judge it by the remainder. So the remainder of this is 0. So it's the same thing as I to the 0. So what's happening here is they keep repeating over and over again. So if there's no remainder, this is the same thing as I to the 0. So they happen by 4. So this one should just be I. I to the fifth. Well, if we do 4 going into 25, I would try 6, and I get a remainder of 1. What's I to the 1? Just I. So I'm just going to say this is I. We're going to do to the 86. All right, so 8 divided by 4. This is 2. Get 6. Try one more. We get a remainder of 2. So we get I squared. I squared is square root of -1 times the square root of -1, which is just -1. So just remember, I is square root of -1. That way, if you forget, if you do I squared, you can just, you don't have to memorize the table. You're just like, oh, I squared, that's just square root of -1 times square root of -1. Square roots would cancel, and you just end up getting -1. So 51. So we can probably assume that this is going to be the positive one. But let's just check, just to make sure. Oh, wait. Why did I put I on that first one? This was supposed to be 1. I'm sorry, guys. So we can assume that's -I. Let's double check, though. So we're going to do this 4 going into 50 divided by, not square root. Goes in 1 time, 11, bring down the 1, makes it 11, 2, 8, and we have a remainder of 3. So we have I third. So I third is the same thing as I squared times I. So I squared was -1 times I. This is our -I. So confirmed. There we go. And then they show you guys the work afterwards. Always, even if you guys get these right, make sure to take a glimpse at these. It does help out, especially if you watch the video, you'll understand why they're doing the 4 times this. This plus 1, that's just the remainder. All right. So give me a second. So here we go here. So again, just doing these I squareds just make it I because the squared would cancel out. So nothing too special about that. If we're using this, what ends up happening, let's say we're doing this square root of -4, we just factor out that I. So we're taking out a square root of -1 because square root of -1 times square root of 4 is the same thing as that. So that's what's happening here. Effectively, this and this are the same thing. So whenever you see a negative, just put an I in front of it and then solve for squaring it. So that's all they're doing right here. They make it all complicated. Basically, if you see a negative, just take out an I and you're good. Here's how we use imaginary numbers. So we're going to take out the I. I don't like how they do this. I really hate this step right here. It makes it super complicated. So here's the way I would do it. If you guys don't like, so this is how they do it. They turn it into -1, which turns -1 is I squared. Square root of I squared is just I, and this. I like thinking about it this way. This is the same thing as I square root of 52. How do we take square roots? We're going to break it up. So I'm going to break this up into, is it 8? Let me think here. I'm going to take out a 2. Take out a 2, that's 56. 2 and 13. Oh, cool. Look, I have a group of 2s. 2I. Oh, this 13, he's by himself. He's by himself. He's going to stay in his room by himself. So couples go outside, singles kind of stay inside right here. That was funny pre-COVID. Now it's just kind of everybody stays inside. But think about it in the before times. Couples go outside, they go out. They go out on a date. And the single stays inside. All right, so this next one. So now we're going to do this expression. So if we do this, we're going to take out the I. Square root of 27. So I know this one's right. Let's see if I can do another one. So then I can do factor tree this 27. I get 9 and 3. 3 and 3. So we get a couple of 3s. They're on the outside. This individual 3, we remember we cross these out once we factor them. Oh, did you like that saying, Nick? That's how I taught my algebra class. This couple goes out on a date and the single person stays inside. What do you mean, Brianna? That what I'm trying to say? Like the lesson doesn't make sense or the joke doesn't make sense? Um, I think it was Sammy who said it in my algebra class. Samuel doesn't even make sense in the chat. Oh, yeah, I get it. Yeah. So Sammy said this in my Algebra 1 class. He remembered this as that Eminem song. Two trailer park girls go round the outside. So they go on the outside. So if you're an Eminem fan, that's a good way of remembering it too. What's up? Yeah. Don't confuse people on the chat, Sammy. All right. So that works out. So that'll help you with doing this. So this is one of the options, and the other options was pulling it out. All right, so we got that. So now we're going to talk about complex numbers. So complex number is this idea of having real numbers combined with these imaginary numbers. And usually the way they want you to write it is they want you to write your real number, your A first. So you're going to write your A first, and then you're going to write your B secondary. So that's how we end up doing these. It helps just because it helps you stay organized, and later on when you need to kind of do things between your imaginary and your real numbers, it really helps split them up. So, as we discussed, a complex number includes a real part and an imaginary part. So A cannot be 0 and B cannot be 0. So obviously if one of them was 0, it would be, so this says if A was 0, then it's just an imaginary number. If B was 0, then it's a real number. So basically a complex number has to be real and imaginary. I don't even know why they wasted time making this slide. I feel it's very obvious. So a number can be real, imaginary, or complex. All right, let's get into the activity. And once we get into the activity, we'll have some chat time. That way Sammy doesn't confuse everybody in the chat anymore. Just to kind of let out that extra energy. All right, so we're always going to divide by 4. Whenever we're doing this, just remember, we're dividing by 4. It's 2, 8. We have a 1. So it's a remainder 1. So in other words, we're going to treat this like I to the 1, which is just I. Then we're going to do 52. So if we do 52, just by looking at it, I'm going to assume it's I squared. But let's go through the process. Maybe I'm wrong. Oh, wait. It is not I squared now that I realize it. Good thing we're doing it. 1, 4, 1, 3, 12. So this is actually I0. I to the 0 is just 1. Anything to the 0 power is just 1. You can also look at it as I to the 4th power, because I squared times I squared is just 1. 4 going into 99. This is I3. I can just tell because I to the 100 is I4. In case you don't know what I mean, that just means that 4 times something equals 100. But just to kind of keep doing it this way, get a 1, 19. 4 going into 19. I'm going to try 4 times. 4 times 4 is 16. I get a 3 as a remainder. So I'm going to treat this like I3. I3 is I squared times I. You can put I1 if you want, I guess. It looks like a negative. That's a dot for the I. So that's -1 times square root of -1, or -1 times I, which is negative I. And then I'm sure you guys are tired of me doing this, so obviously this is the last one. And you can always look at the work just to get a confirmation. They're basically just dividing it. So this was my divide, what I got when I divided. And this right here is my remainder. The remainder is the only thing that really matters, to be honest. Oops, went through it too fast. So real number or imaginary number? Okay, so if we square this, the square and the square root cancel, so we end up getting a negative x. Because what's happening here is we square it first, so we get 25, which is just 5. So this is a real number. It's trying to trick you. That square inside kind of cancels out. Well, this one's obviously a real number. This one is a complex, it isn't a complex number actually. This I squared makes it -1. So this is actually a real number because I squared equals -1. So this ends up being -10. So they almost got me on that one. It's a negative number, but it's still a real number. This one, this actually doesn't belong. Drag the tiles, classify base, real or complex. They made that slide, and I have a feeling they're going to mark me wrong by not picking a spot for this. This is a real number because if you do it divided by 4, it's I0, which is 1. This is an imaginary number. This is an imaginary number. These two are complex. Oh, these are just imaginary numbers. This is the only complex number. These ones are only imaginary numbers, so they're being hypocrites. Ignore that one slide, guys, that said the 0 thing. Ignore this slide. They've just been hypocrites right now. So give me a second. This slide right here, because now they're saying imaginary numbers are complex. Oh, can be considered complex. Oh my gosh. So what's the point of this slide? Wow. All right. So complex numbers have some kind of imaginary number, guys. There was no point in that slide whatsoever. So real, real, real. This is imaginary, so it's considered complex. This one's real because it's I0. 8 goes into 4, goes into 8 perfectly. This is imaginary. This one's complex. This one's imaginary, meaning it's complex. So there we go. I don't know why they have that slide 19. It's kind of pointless. So here we're going to split this up. So the first thing we're going to want to do here to get rid of this is we're going to pull out that I. So we're going to pull out an I. Well, they call it a -1. We can call it just I. So, oh, they already put the -1 there, which I think is dumb. They should really call it I. So we're going to pull out an I. And this will just be 12I. Cool. Another thing you guys could have, well, I guess you do have to do it that way. I don't like this step. I think you should skip this step and go through this stuff. When you're showing your work for the unit activity, feel free to skip this step. I always just say, like, just take out the I. So much easier. I see a negative, just take out an I. All right, so let's get down to this. So this, you guys might remember this from the quadratic formula. It's a simplified quadratic formula. -b plus or minus square root of b squared minus 4ac, all divided by 2a. In this case, I'm assuming that the a was 1 and the b was -4 and the c was 5. That's just a pattern I see. If you guys don't see that, that's fine. And they're only doing the positive version. So they're getting into this a little bit early because we will eventually have to use imaginary numbers with the quadratic formula. That's why they're introducing you to something that looks like this, because it's based off of this. All right, so let's get into this. So what we're going to do here, we are going to leave the 4 where it is. Well, first we have a fraction. Leave the 2 is just fine where it's at. Oh my gosh, I have to use arrows. The 4 is just fine where it's at also. The square root, we'll leave that there. Leave the 16 minus 20. If you're lazy like I am, I just copy this, put a little equal sign here, paste it. Now inside the parentheses, I'm going to get this -4, this -4. After that, you can do this, paste this. We can change this to, we're going to take out an I. So this is what I meant by you guys can skip a step and just change this to 4. From here, we're going to get this 4 plus 2I. From here, you guys don't have to show this step. I recommend it. It's having 2 different terms. Like I said, you don't have to show this middle step. I'm just doing it for your guys' benefit so you guys can see where it is. If you want, you guys can go straight to 2 plus I. And I have a feeling because this is a graded activity, they only want you to do the 2 plus I. Yep. I really hate these because then you guys forget that you're supposed to show your work for the unit activities. So this is just 2 plus I. They even show all the work here, but they don't accept that as an answer. So always do your work on scratch paper. In part, simplified expression, what type of other expression does this remind you of? So this reminds me of the quadratic formula. That's what this reminds me of. And I'll probably mention it here too. The expression is similar to the quadratic formula. So whenever we get this inside part negative, this part right here, I don't know if you guys want to write this down. I recommend it. This is known as the discriminant. If the discriminant is negative, that means we're only going to have complex answers. If we get a positive discriminant, we're going to have two real solutions. And if our discriminant is 0, then we only have one real solution or one solution. It just doubles up. All right, and then just write what you guys think here. This one, I would probably give myself a lower score because I would be like, it was frustrating showing all my work and it just wanted the answer. It really should specify that it wants the answer. So that's all we'll cover for today. This Tuesday, we will cover the remaining half.